release at the end of June, and also a virtual conference in August. So stay tuned. So without much ado, we'll hand over to Dr. Winfred Amarko.
Great. Thank you very much, and welcome to today's webinar. So both speakers are well known to you, but I think some of you may not have interacted with Karen for a while, because Karen returned to the US and is now working with USAID as a specialist. But before that, she spent nearly 8 years in KNUST as an associate professor. Karen is going to tell us. Would you like to start, Karen?
Sure.
Yeah. And so we will take questions and discussions after both speakers have given their presentation. Karen, thank you.
Okay, great. And I want to emphasize, please, keep me on time. I'm aiming for no more than 30 minutes because I'll even try to cut down now to maybe 20, just so we can have both speakers, have some introductory material and we have time for dialogue. So I've titled this Virology 101, everything you always wanted to know about coronaviruses, but were afraid to ask or didn't know you should ask. Now, what I want to say is anyone who wants today's presentation, feel free to reach out to me. My email is karen.duca@gmail.com, but you can get it from anyone associated with COBREG. I put this together last year, but it's still very relevant. I've been tapped quite a bit to do webinars. I used to work in the coronavirology field, and sad to say, at that time, it was a backwater with very few of us. It was a niche area, no longer. So in this presentation, and I'm happy if you're a lecturer and you want to use it with your students, if you're a student and you want to do outreach to K through 12, by all means, please share these. Most of this material is publicly available and was gleaned from internet sources. So what I want to focus on today is what viruses are. And I will use two examples, both of them caused a global pandemic. I'm going to obviously talk about SARS coronavirus 2, and the other massive, devastating global pandemic a century ago was H1N1 influenza. And I've really been a student of that pandemic, and much of what we learned then has stood us in good stead in this current pandemic. The slides include a little bit about viral pathogenesis, but I think I'm going to leave that. I'm going to leave most of that out and just briefly touch on a couple of things. Joe will handle that. He's far more in touch with the clinical manifestations than I am. But what's really critical, and I think very few people appreciate this, even virologists, is how do viruses evolve? What do we know about that? And can we predict what will happen with SARS coronavirus 2 in any given detail? We've seen enough evolution even in this, 16-month pandemic time frame, but where is it headed? And there's also a little bit about the epidemiology, and there's a little bit about vaccine technologies in this presentation, but that I'm going to skip over. Okay, so first of all, what are viruses? Okay, for a long time, it was debated whether viruses are even alive. These are biological entities that are essentially nothing but a small piece of genetic material. It can be either DNA or RNA. It's wrapped in protein to protect its integrity, and some are wrapped in lipids, okay? Those are called enveloped viruses, and SARS coronavirus 2 is a lipid encapsulated viruses. Now, outside of a host, a virus is as inert as a rock. It does nothing. And enveloped viruses like SARS coronavirus 2, they have a very short lifespan environmentally because they dehydrate. Viruses that are protein encapsulated, like smallpox, have a much longer lifespan. And this, I want to start like referring to some evolutionary aspects. In our early history, when population was very low, viruses had to survive in the environment. Okay, if they couldn't survive in the environment, if they couldn't find a new host rapidly, they disintegrated, they were gone. So you tend to see the more stable viruses, they tend to be more DNA based, and they tend to be coated in protein. They don't have lipid coats. The more modern viruses, things that are emerging now, we are 7 billion plus people on the planet. It's very easy for viruses to jump into us. So they tend to be more physically fragile because they can be. They can still spread and replicate without a lot of protection to their own physical integrity. Now, as obligate parasites, they need that host, and they hijack the host's machinery to do nothing but replicate themselves. That is all they do. They replicate. Now, all living organisms have viruses, including bacteria and protozoans. And viruses have what's called a host tropism. So not every virus can infect every organism on the planet. Now, within a susceptible host, only certain tissues can be infected, and this we refer to as tissue tropism. And tissue tropism is determined by cell surface receptors that permit the viral entry. Now, we often talk about the VAP, the viral attachment protein, on the surface of the virus. It's looking for its host receptor to be able to signal internalization. Now, I've just shown, our two culprits responsible for this global pandemic. On my left here, we have the coronavirus. You see the viral attachment protein, which is the spike glycoprotein. And here you see it in an electron micrograph. Now, the influenza virus is quite different, okay? But it has its hemagglutinin, and this is its equivalent of the S protein. It's its viral attachment protein. It also uses the neuraminidase to do, this does some cleavage at the receptor site, which is sialic acid. And this helps the virus internalize by a very interesting mechanism. And here you see the influenza virion in an electron micrograph. And what's interesting, notice you always see this spiky appearance on the surface of an envelope virus, because what it needs to attach to its receptor is very prominent. Over here, you can see them a little bit less densely packed. And they get their name. Do you think this looks like a little crown? Corona actually means crown in Latin, and that's how they were so named. Now, I wanted to just show you a little bit in more depth, what the genome looks like, okay? So this is a generic coronavirus. This is not necessarily SARS coronavirus 2. It's in the family Coronaviridae. These tend to be fairly large genomes, large virions, large genomes that need a large virion to get packed into, so 120 to 160 nanometers. It's a positive sense single-stranded RNA genome. And it is itself. What does that tell you? Because it's a positive sense, it is literally one gigantic messenger RNA, but that is not its normal replication strategy. It doesn't get into a virus and it doesn't get into a host cell and start replicating from its genome. It will make a negative strand copy of itself, and then from there make another positive strand, and that will be cleaved as messenger RNA. And it has a so-called nested genome. So the RNAs sometimes they overlap each other. They're not distinct, arranged along the genome. Now, the influenza virus is quite different. Okay, it's a negative stranded RNA genome and in a smaller virion, 50 to 120 nanometers in diameter. Also lipid enveloped, but it's segmented. You could almost think of these as chromosomes, if you will. So because it's segmented, this gives it different kinds of evolutionary options that are not available to this coronavirus. Now, as you've probably heard, there is a certain amount of editing in this RNA genome. There is some exonuclease activity. What this means is when the virus is copied, it does have a small ability to correct mistakes. Nowhere near as good as, say, the polio virus, which is amazingly good at replicating itself and which makes it a very easy virus to raise a vaccine against. Influenza, a much more challenging virus to raise a vaccine against because it evolves. It does not have RNA proofreading capability in it. So it drifts genetically quite a bit. And it's got this segmented genome, which means if an organism is infected by two separate viruses, these different units can recombine in unique ways and make different viruses that we haven't seen before. As far as coronaviruses, all these guys can do is standard recombination, and that can only happen when you've got two different viral genomes in the same cell, and there's a crossover event. Okay, so these are kind of two ways that the virus can alter its genome beyond just point mutation. Okay, now the key thing here is, what does a virus do when it gets into a cell? What's the life cycle? Okay, there are two things happening. So a virus first has to attach to the cell surface receptor. And as we know, for COVID, this is the ACE2 receptor. It penetrates into the cell, and this is normally, it hijacks the normal endocytic machinery. It doesn't just sort of penetrate that membrane and go through. It is internalized in the normal membrane recycling process. So once it's into the cell, the endosome uncoats, right? And it releases the genome. Now, what'll happen next, because coronaviruses, these are just gigantic long messages, as I said before, what it'll do, it's then going to make a negative strand copy of itself. It will then, from that negative strand, make the messenger RNAs. Now, that is how flu does it. Because flu is already negative strand, it can't copy itself directly anyhow. So what flu does, it'll make positive strand copies, which are the messenger RNAs for the viral proteins. They will find ribosomes and they will start making the viral proteins. Now, these viral proteins will be trafficked normally through the endoplasmic reticulum and outside. They will translate to the inner surface of the membrane where they will pick up their genomes. The genomes will, these proteins are such, the ones that are closest to the genome are designed to recognize those sequences of bases and fold properly. They will then internalize, pick up some lipid, and then bud out in the normal process. And what you normally find, one cell can generate thousands of virions, and it is a sloppy process, right? There are mistakes that happen, point mutations. There are poorly assembled virions. Some of them don't have all the proteins in them. They don't have complete, they have partially produced genomes. So there's a lot of errors here. But the thing that matters, there's enough viable virus to infect the next cell and to be excreted by the host. Now, what's going on when this process goes on? And let me say something interesting to compare like the coronavirus with the flu virus. Most viruses replicate in the cytoplasm, and they use the cell's pool of nucleotides and amino acids to do their thing, and they effectively exhaust it. The influenza virus is interesting. It actually replicates itself in the nucleus, and it needs some of the ribozymes in the nucleus to be able to, to duplicate itself. So that's a pretty rare situation, and it replicates in the nucleus, and there's a lot of traffic between the nucleus and the cytoplasm with influenza. But once it's made its genome segments, it buds out just the same way as the coronavirus, taking a little bit of the membrane out with it. Now, the cell is not sitting down doing nothing, okay? The minute a foreign entity enters this cell, they are recognized as foreign, and the cell itself begins mobilization of the immune response. This is what we call the innate immune response. And this is something that can go horribly wrong in both flu and COVID to cause disease. So what happens is the cell starts producing interferons and other pro-inflammatory cytokines, and it initiates the apoptosis program, which may or may not be overridden by viral proteins. Both of these puppies can override apoptosis and disable that system. Okay, I just updated my slide just to show you how successful this virus is. To date, we're looking at 133 million cases, and that's just the ones we know about. We're estimating that there could be really tenfold or more cases. And sad to say, global deaths are approaching 3 million, and that is certainly also low. I'm going to skip over this. One thing I want to say, just one word about viral pathogenesis. It's a complex equation that involves both the host and the virus. On the host side, the overall state of health, underlying vulnerabilities, prior exposure to pathogens, your own particular protective SNPs and haplotypes, which we have identified for viruses, have a role to play, right? It's not that it's intrinsic to the virus. It's a dance between the virus and the host as to what happens. And I think we've all seen that outcomes in COVID are very variable. Now, to this day, the pathogenesis of 1918 influenza is poorly understood, and COVID-19 is even less understood, although SARS gives us some clues. So I'm going to just jump ahead and say that what's involved is manipulation of this very early pro-inflammatory signaling, the interferon alpha pathway. Now, I'm going to skip over this too. This is, okay, let me just stop here. What both of these do, I'm sure you've heard talk about a cytokine storm, right? The viruses manipulate the levels of TNF alpha, interleukin 6, and interleukin 10. And they don't signal properly. The innate immune response entrains the adaptive response. So there's signals to start this process. And if you jumble up the signals in a crazy way, which both of these viruses do, the immune system doesn't know what to do next, and you have a kind of runaway viral replication. And this is part of the pathogenesis, not the whole story. So I want to just touch briefly now on viral evolution. And I think we all know, we're all scientists here, so we understand that RNA viruses are a little sloppy in their replication. Okay, I'm going to skip through this. I've got some references, a really wonderful article in the New Yorker magazine. All of these are free to get. This field is very mathematical and rests on a lot of theoretical models and assumptions about mutation rates of the nucleotide bases. But there are a couple of things that are really critical to know. What we think is viruses mutate randomly, and most of the mutations are lethal. They're not successful for the viruses. And all the virus wants to do, we've had some really interesting breakthrough work by an evolutionary biologist called Paul Ewald. I really want to send you to his TED Talk because it's valuable. And his thesis is that pathogen evolution depends on its route of transmission. If transmission is host to host, the pathogen needs the host to be mobile, it doesn't generally hurt the host as much. If transmission is through water or air, the pathogen doesn't need mobility of a host. It can still be very virulent and still reproduce. We used to think that hosts and viruses co-evolved to sort of a commensal, kind of let's live together and get along. That is not true at all. The evolution tends to move a virus towards intermediate virulence, but what the main goal here is transmission. And now this is the last thing I want to talk about. The way viruses exist, they are what we call a quasi-species. An initial founder virus will get into a cell, and it will make some mistakes. All of these little symbols represent an error in the reproduction of that genome. Now, this is going to spread out and it will fan out, and over generations, more and more of these mutations will get picked up. Now, what happens is the ones that are successful, most will die out, but the successful ones that can outcompete the parental strain will eventually become the dominant ones. And this is what has happened with the B117, the so-called UK variant, the South African variant, the Brazilian variant. The variants that have emerged are just more successful in replicating, in getting into the host faster, and they outcompete. There's no, shall we say, this isn't a directed process. It's just very lucky, okay? Now we have at least 100. This was when I made this slide, which was nearly a year ago. There are at least 103 circulating variants that we're aware of. We have 2 major families, and this is on the move, okay? It's happening all the time. Now I'm going to skip this. You can look at it yourself. Same thing, influenza is a very similar type of process, but what's very scary here is if you get a dual infection, you can now mix strains in ways that they haven't before, and this is how we believe H1N1 1918 evolved, and we now believe it began in China. We used to think it started in the US. So that was kind of fast, but I definitely want to, make sure I finish on enough time for my colleague and so that we have questions. So that was a little bit of a quick pass through viruses and viral evolution. And I'm happy to have anyone reach out for more clarification. And you're all welcome to have my slides. Let me stop sharing right now.
Thank you very much, Karen. So I will take questions later on. So it's my pleasure to introduce Dr. Joseph Boni. Again, he works in Kumfa Noche. He's a UST graduate and is a specialist in emergency medicine, I call it. But he also has a management training. So you've spoken to us before, and this is a follow-up of what is currently ongoing. Joseph.
Hello, can you confirm you can hear me and see my slides, please?
Yes, I can hear you, but if you go to slide presentation, I can see the slide, but it's not in full mode.
Right, let me work on this.
But I suppose if the others can see, I have no problem.
Hello, can you hear me?
Yes, indeed.
Right, sharing my screen now.
Great.
Okay, thank you very much. Sorry for the little technical delay. So my name is Dr. Boni, and then I'll be talking to you about COVID-19 research and measuring the roles of vaccines in reducing the clinical burden for COVID-19 disease. We're not going to be very long on this, as we said before, to provide time to take questions after this presentation. So we would want to start by talking about vaccines. So what are vaccines in general? But before we can talk about vaccines, we need to learn about what the immune system is. So just a few slides, we'll just give a quick summary on what the immune system is. So the immune system is the defense mechanism for the host. And Karen already touched on how the virus is and how the virus behaves. So your immune system in a perfect world, well, you have the bad organisms separated from the happy people. But this is the real world where we have them mixed up with us, and there's always a war between your body and some organisms that are affecting you. So your immunity can either be innate or adaptive. And for your adaptive, you can have your natural.
I think you've dropped. Dr. Boni, I think you're frozen. I might have to re-enter.
I don't think you have to re-enter, Winfred.
No, I'm okay.
Yeah.
I meant Dr. Bonnie.
Oh, okay, sure.
Yeah. You're back? Ah, great.
Hello. So sorry about that. I had a problem with the connection.
Yeah.
I'll restart my screen share and continue from just where I left off.
Thank you.
Can you confirm you can hear and see the screen now?
Yes, I can. And you are in motion.
Excellent.
I can hear you.
Thank you very much. Apologies for that. So I talked about how the immunity is broken down. So active, innate, and then you can have the natural, which are passive from the maternal end, or the active. And then for the artificial ones, you can have direct antibody transfers or active artificial immunity, which is when you are immunized. So then what are the vaccines? So the vaccines are biological preparations that provide active acquired immunity to a particular disease. So in a sense, it's a weakened form of the virus that's introduced into the body. It can either be the microbe itself, its toxins, or one of its surface proteins that's introduced into the body. The body then recognizes, immune system recognizes the threat, destroys it, and then literally keeps a memory of what that organism is in order for it to be able to do the same action if it is attacked by the organism again. So here is a diagrammatic representation. So a weak or dead form of the virus is introduced, it sparks the immune response, and the antibody fights off these organisms, but retains a memory of how this was done. There is a lot of information about vaccine development, and I just want to use this to show that there are various stages from the preclinical phase, phase 1, phase 2, phase 3, and then finally phase 4. So it's around phase 3, after phase 3 that we would get registration with FDA, and phase 4 would be after it is out there, looking at the market and seeing how efficacious this virus is in a population. And when we talk about the new goals and ambitions to reach this new vaccine, usually it takes quite a long time for you to be able to develop a vaccine. But with COVID-19, looking at current presentations showing the reach of the virus and its direct effects on people, there had to be increased efforts to get these vaccines out. So we had a lot of dynamic leadership and governmental involvement, extensive stakeholder collaborations, data sharing from a lot of countries in the world, and extensive global collaboration, along with multiple streams of funding to get this work done. The diagram here shows the required funding that had to be put in place in order for us to be able to get the vaccine at this stage. So there are lots of information going around about what vaccines are and what they are not. So let's start with some of the truth about vaccines. So vaccines are not drugs, and they do not work like drugs. People sound like, when I take the vaccine, I will be healed. But as we already explained, the vaccine will then teach your immune system how to fight the disease a little better. The vaccines do not kill pathogens, but rather they can be used as training to aid the immune system, as was explained earlier in the diagram. Vaccines are safe for use in children, and they need it most. And this is talking about vaccines in general. And we do remember child welfare clinics where children need to go to the clinic and either get immunized with an injection or oral drops. And vaccines are significant health interventions for people living in resource-limited settings. So if you're in a setting where your healthcare system can support the disease you have, then your need for vaccines are less significant. But in a place where your health system might not be able to support when you do get the disease, then your prevention is really key to ensure that you do stay healthy even when that disease is around. Then vaccines can be used to prevent a lot of diseases, especially those that have no cure. And this is very important. We have seen eradication of some conditions. Smallpox is a common example. And in Ghana, at some point, we were able to push polio to a barest minimum, although now we still have polio rearing its head again. So the relevance of a vaccine, and I have summarized all of this in just this. So it helps to prevent the disease. If you have taken the vaccine, you are prevented from getting the condition itself. Also, the vaccines can provide herd immunity, and the picture up here shows a lot of people holding a shield to protect all the people in there. If a lot of people are vaccinated, it breaks the chain of transmission and then reduces the disease burden entirely. Even if you were to get the disease when vaccinated, and in our case, COVID-19, it helps reduce the severity. And this has been seen in many countries as they continue to promote their vaccine campaigns to show that people are still getting COVID-19, but the severity of the disease is significantly reduced, along with a reduction in the mortality. So all of this is great, but then how do you measure the clinical picture of COVID-19? Are we able to find out really what is happening? So the next session of my presentation will talk about some of the research work going on to measure the clinical picture of COVID-19. The first I will speak about is the clinical characterization protocol. The clinical characterization protocol has been designed for severe and potentially severe acute infections of public health concern. This was initially designed by ISARIC and then has been modified to fit the COVID-19 presentation. So why is a clinical characterization protocol important? So if we take these silos as either various hospitals, various regions, various countries in the world, if everybody's collecting information about COVID-19, this information just stays with them, and this information might not be standardized. But what happens when you use the clinical characterization protocol system is that because this is standardized across areas, we're able to form a bridge across all these institutions where information can easily be shared and data can be shared and collaborated. And with this, you have the solution of being able to compare data, have large data sets, which can help in the development of vaccine, development of screening tools, and development of laboratory investigations, and increase the impact for this. So I already talked about this being a product from ISARIC, which is the International Severe Acute Respiratory and Emerging Infections Consortium, who helped develop this. And this has been adapted in Africa. This has been adapted through ALERT to be able to provide Africa-ready documents. And this has been shared and it's in progress in a lot of African countries. The process that this goes through is you have to look at going through ethics, data collection, employment. You talk about the comorbid conditions, if they had any imaging done, mental assessments of the patients, and then data. All of this data is processed through REDCap and then eventually analyzed for this. With this, we have had to be able to build some experience with challenges of being able to get research work in COVID-19 done. And this challenge doesn't only apply to the clinical characterization protocol, but can easily be expanded to all other research work to be able to measure the impact of COVID-19 or the clinical picture of COVID-19. The first one is ethical clearance delays. COVID-19 put a stress on every institution, and this includes ethical clearance institutions. So ethics boards were not meeting as frequently. A lot of them had to progress and use Zoom, which was new to some of the ethical members, and this put a strain on the ethical committees. Then the implementation and training. Now we have to train people on how to use tools, then the risk of putting people together to train them also became a concern. Already, training and implementation comes with its challenges, but when you throw in COVID-19, it just made it a little more difficult. COVID-19 really took a political turn where countries wanted to show they were safe. We're not sure if we're reporting all the values in one country or the other, all the deaths being recorded. So if you ever said you were doing a work in COVID-19, you had to ensure that you got the political buy-in to get this done. Collaboration and resource mobilization also became a concern. So people had to work around consortiums and fundings to get this together. Then tools and technology needed to be upgraded in order to ensure that capturing data from COVID-19 positive patients did not put the researchers at risk. But what was more important was the quick and relevant outputs. If you're collecting data for a condition that kept evolving and everybody wanted answers, it couldn't be research as usual, where we collect the data, store the data, analyze it, and come out with a report. But to be able to produce dynamic outputs for people to use this, and it was clearly a race against time. The next few slides just talks about some of the practical solutions to these problems, which I have discussed as we moved through these. The output of the research is supposed to ensure that we have clinical characterizations for COVID-19. How does it present? How does it present in Ghana compared to Nigeria, Italy, China, or Australia? Then the long-term effects of COVID-19, which has now become very topical. What is long COVID, as it's now being called? What are the effects of people that were positive? And what is the immune response? How long does your immunity last? And what are the other interventions? An example is for steroid use, which has clearly been shown by the recovery trial. This slide shows an example of the dynamic outputs that we would want to promote among COVID research. And this is what is being done by ALERT with the Global Health and Infectious Disease Group at KCCR being the hub for supporting this work all over Africa. The data collected in REDCap dynamically produce these outputs, and these can be shared with all the agencies who are relevant in COVID-19 management to be able to use the data collected to make informed decisions. But a big part of COVID-19 work has to do with healthcare workers, and finding out what the healthcare workers think about COVID-19 also is a really big part of COVID-19 research. And now, one of the big questions is, are health workers happy to take the vaccine? And developing research tools and surveys for health workers is really a big part of how you can measure the effect of COVID-19 and how the health workers are coping with the effect of COVID-19. This shows a schematic of a tool being developed simply through either Google Forms or REDCap, and this can be tagged with a CPD or a CME in order to encourage health workers to complete such forms. In a survey that was done in Ghana for health workers looking at their involvement with COVID-19 and the effects of infection prevention on COVID-19, we had over 4,000 responses, and this was really significant, showing the number of doctors, nurses, allied health, pharmacists, and physician assistants who answered the survey. Then the big question is, how many people actually did get COVID-19 and did not know about it? So another huge research area for COVID-19 is the seroprevalence, where you will be able to judge how many people have antibodies to this. So this is really interesting, where personal experiences, I tested positive for COVID-19, but then I have co-workers who never tested positive for COVID-19. But when we did a seroprevalence test, we all had antibodies at some point, showing that even those that did not show symptoms were positive for COVID-19. This really becomes significant because as we look at the world numbers, the question is how many people were positive but never actually had symptoms or tested for COVID-19 whilst they were positive. So a seroprevalence looking at antibodies for COVID will give us a true picture. The next slide shows a schematic of work being done by my colleague and at KCCR showing the schematics where we go out in the field to collect data. This data is brought back to the lab and it's processed with an ELISA to show us how many people actually had antibodies against COVID-19. Off the top of my head, I think that the current prevalence we're looking at is between 20 and 30%, and the work it's going on, and this is work that is going on at KCCR with the Global Health and Infectious Disease Group, headed by Dr. John Amoesi and Dr. Anthony Ejeyefumpewa is the PI for the study looking at serological tests. Aside the work happening at descriptive work and investigative work happening, clinical trials is also a big part of research to be able to get a clear picture of what is happening. So we're very happy that Ghana is hosting the anti-cough trial, and this is being hosted at Komfo-Anokye Teaching Hospital. The aim of this research is to be able to find out if there are any therapies that can prevent you from moving from mild conditions through to moderate to severe. So which medications can we give you when you have COVID? And this answer has really not been found. If you had COVID, we gave experimental treatments and hope it will work. Recovery trial has been able to tell us that if you had severe COVID, steroids will be available to help protect the severity of the disease. But from mild through to severe, there hasn't clearly been a medication. So this trial, which is happening in 14 African countries, and luckily Ghana is one of them, hosted at the Komfo-Anokye Teaching Hospital, is looking at people that come in with uncomplicated pneumonia. And if we gave them some arms of medication, which is now nitazoxamide and cycloxanide, whether it would prevent them from progressing to severe disease. If you did progress to severe disease, then you can be recruited for a recovery trial, which should also be starting in Ghana very soon under the same research group. All of this research work would have started before the vaccines came in. So now what are the vaccines doing to the research work? Initially, this is the schematic that we had. We had a global health emergency, a lot of research from all rounds going in to improve healthcare and to promote the development of treatments and vaccines. Now, this has clearly turned. We do have the vaccines, and now we need to look at the effects of the vaccines through research work and how this affects the improved healthcare. So thank you very much for giving me the opportunity to share the experiences of research and how to measure COVID-19 through research work. Thank you. And I just want to leave this slide just to show my affiliation to Komfo-Anokye Teaching Hospital, where I work as an emergency medicine specialist. And I'm also a research fellow in the Global Health and Infectious Disease Research Group at KCCR. Thank you very much.
Thank you. Thank you very much. So there are a few questions in the chat, which I will read out to you, and either of you may wish to answer. So the first question is, how many people should be vaccinated to achieve herd immunity?
I can address that from a modeling standpoint. And I will say one interesting thing about this is epidemiology, and some of these modeling efforts have progressed a decade in the last year out of necessity. So what is normally, the way this is normally calculated, the number of people that need to be immune is directly related to what we call the reproductive ratio, which is how many people one person on average does infect. Now, let me tell you, one of the highest reproductive ratios we have is measles, okay, very high. And for measles, you need 95% of the population to be immune. This has been observed experimentally. Now, there have been new modeling studies that have suggested as few as 30% of a vaccinated population will generate herd immunity, and we know that to be false. because we have countries now with very high levels. Israel is the poster child of very effective vaccination, and it seems they are, I believe, at about 75% vaccinated population, and they are seeing their cases plummeting, and they are like they were a year ago at the very start, very, very few cases. So it looks to be, it's got to be pretty high. And the original prediction was between 80 and 90%. And I think we are still at that level. I mean, it's definitely going to be above 70%. But here's the problem. We do have, as Dr. Bonnie said, you can achieve immunity through natural infection or through vaccination. And we know that natural infection of mild and moderate stripe aren't very effective at preventing reinfection. They can, but they're not great. Vaccination is far better. And we have a lot of vaccine hesitators. So once we're in the 70s, I think we're going to see considerable drop in spread, but I don't think we're ever going to get enough of the population anywhere to agree to take it. So we're going to have to live with this virus at a steady state for some time to come. Joe, can you add on to that as someone who's really on the front lines of vaccinating and dealing with people's attitudes and such?
All right, Karen, thank you very much for this. It's actually become quite clear that we do have a lot of vaccine hesitators, and even in the hospital among health workers who clearly see the direct effects of COVID-19, we still have people that are really hesitant to take the vaccine. And as Karen said, if we don't have that high number or percentage of the population, then herd immunity becomes very difficult to hit. So I think Karen explained with the modeling what numbers you need to require for this. So there's not much more I would have to add. Thank you.
So I'll just add, I think it's important that we achieve that herd immunity but through vaccinations, because as Karen said, the mild to moderate infections don't give you that, that good protection. And there are cases reported, a few cases so far of reinfection with COVID. So that which confirms that you need the vaccination to make things work. Now, unfortunately, there is a lot of mis or disinformation, which is why people are hesitant to have vaccinations. But the government everywhere, I believe, needs to educate the population and burst these myths about infertility from vaccination, being tagged with different things so that your position anywhere can be detected, you're being followed. It's all sort of silly things around. So I think it's important that we, as as a group and as individuals, try to educate families and friends as much as possible to burst some of these myths. Okay. So there's a question which says, are current vaccines useful against all viral variants? Would you like to pick that, Karen? Or
well, I can say from what I'm reading, so far so good, at least to some extent. And there was a paper that's recently come out in Science. We were concerned about that UK variant, and it seems that the T cell response, the antibodies that the current vaccines generate aren't as good against that variant, but the T cells are doing the job. So as you know, you can have either a B or a T cell response here. And so far we're in good shape. But let me chime in with something about viral evolution that does concern me. I was worried about the rate at which we're vaccinating, because partial vaccination, this is exactly what I would do if I wanted to put evolutionary pressure on the virus to change, right? The virus responds to things that try to drive it out of the system, right? So I wanted to see us vaccinating rapidly because we are going to see vaccine escape mutants. We will see those mutations. And the companies are already working on second and third generation viruses to boost once we have. I mean, we're going to drive out the initial variants with vaccination, that's clear. But the new ones, and children are a big reservoir. This is what I'm waiting to see, that there'll be a mutant that is more infectious for kids because no vaccine is approved for younger than 12 years old right now. And they are protected. They don't have as many ACE2 receptors as adults, but they do have them.
And yes, disease has been detected in kids, and as you said, most of the time they are asymptomatic. So, and they pass it around freely.
Yeah. Oh, kids were the driver of the 1918 spread. I mean, kids are the primary reservoirs. Their immune systems are weaker. They let the virus replicate to higher titer. Yeah. And hey, I'm just impressed that our tribe of scientists have done so well. I'm amazed, and just this would have been a dream for 1918.
Yeah.
But nonetheless, there's more work to be done, and I think all of us are online all the time trying to debunk crazy ideas and wrong notions, because right now vaccination is our only hope of getting to herd immunity. My fear is we won't get there. My fear is we're going to have to, we will reach steady state where I think my prediction is we can't eradicate it now. There were moments when, had we done certain things, we might have really eradicated it the way we did SARS and MERS. But now it's too late. And we will have it as a low level, steady state thing like we have influenza. I just want it to be lower rather than higher. That is my hope. I hope I'm wrong. I don't know. What do you think, Joe? Do you think we'll get there? Or?
Joe, what do you think?
Karen, you put in a really good point. Karen really puts in a really good point about how the risk of us being able to have the virus mutate to the vaccine, and as quickly as we are able to work on the vaccination being everywhere, the lower chances of developing variants that the vaccine might not be as effective to. So we do have a comment and another question in there asking about the current vaccines against the variants. So I did just put up the slide to show the number of vaccinations we have done in Ghana so far, and then looking at the various type of vaccines that are available. Already, these have all shown to be efficacious with probably different levels of effect on the virus, but then we have been able to identify that all these are efficacious and working well. This chart shows the percentage of countries that have been vaccinated or with ongoing vaccination. And this shows clearly that there's still a lot of work to be done, as most people are falling in 20%. So it becomes a little difficult for us to be heading towards herd immunity right now. Thank you.
Okay, so there's a follow-on question, so which says, is the pandemic over? But I'll leave you to paraphrase that.
No.
So
I think Karen just said it. The answer is no.
Yeah. So unfortunately, well, I'll add more perspective to it. So unfortunately, no, and COVID is going to stay with us for a while, unfortunately. Now, in some areas now in Europe, wave 3, the high infection rate is occurring at the moment. And even in UK, where vaccination seems to be better than elsewhere in Europe, we are predicting there might be a wave 3, probably in July, August, if things don't go the right way. So unfortunately, the pandemic is not over, and people have to be on the lookout. We can't become complacent, unfortunately.
And I think we've got to, all of us, really talk to our friends. I've not been happy sometimes about coronavirus media. I've not been happy. I think it hasn't been respectful of the public's tolerance for ambiguity. There is indeed much we don't know. And, um, you know, we have changed our thinking from the beginning. Remember, as someone who has studied coronaviruses, I never really believed that surfaces were a strong source of infection, right? I mean, that never seemed logical to me. And the amount of spread that was happening even early was too much from touching surfaces. Now we know that influenza does spread a little more than surfaces, but today our thinking is that surfaces don't contribute at all. And yet all of us are still disinfecting. We jokingly are calling it disinfection theater, right? And do you want to do it for show? Granted, hand washing and other kinds of hygiene, they're great for preventing spread of all kinds of viruses. As we've noted, we've had the mildest flu season in years, metapneumovirus, lots of other things have gone way down as a result of this, but corona is primarily an airborne transmission. And I think because we tried to project too much certainty early on, that's where people started losing faith in governments and public health authorities. I mean, it's my sense, that if we had been a little more open about this is all brand new, this is what we think, stay tuned for possible changes, I think the public would have stayed on board a little bit longer. But I deal constantly with people who feel they can't trust anything that they hear out of the US CDC and even globally around the world.
Yeah. Yeah.
I
So
don't know if others have that sense, or they were happy with their country's communication strategies.
I think very few countries were, even in the UK, because the sort of dithering at the beginning and the frequently changing messages did not help at all. It's made people sort of not believe everything they are told, and sometimes they just flout it. We're just coming out of our second lockdown. Well, third actually. We're just coming out of the third one. Shops have been closed apart from essential food until next Monday. So we've been in lockdown for the past 3 months. So and unfortunately, because the infection rate is now low, people think, oh, they can start breaking some of the rules before the lockdown is finished. And unfortunately, that might spread more disaster or, mean disaster in the future. But let's hope it doesn't happen. So there is another, is everything we know about viruses now, is COVID-19 just a warm-up for something more deadly? I'm sure you love that one.
I think I'd like to take this one. I think from my background with emergency medicine and disaster medicine, I think we should always just plan for the worst. This could be a warm-up, but this could also be a wake-up call. It brings in the evidence of our relevance towards disaster medicine and public health
There is a
and infectious
background
disease,
noise.
and also in One Health. Is it better now?
No, I don't think it's you. Joe, you're muted.
You're muted.
Okay, is it better now?
Yep. Are you still muted?
Okay, so
Sorry.
the idea is to look at this as a not as a warm up, but as not as a warm up, but as a time for us to set up and look at interventions to prevent the next infectious disease. With the background in disaster medicine, this is our chance for us to look at mitigation. How do we mitigate the next infectious disease, and will we be ready to fight the next infectious disease? That's my answer.
Okay, thank you. Any additions, Karen?
And I would say, generally speaking, I always come back to viral evolution. A virus is not interested in killing a host. It's interested in manipulating a host. And in the US, as Dr. Bonnie said, we are getting some treatments. We're learning that steroids are good. And the case fatality rate in the US, if you have active COVID, non-asymptomatic even, it's 0.3%. It's not terribly lethal, okay, in terms of compared to SARS and MERS, which were very, very fatal, but they didn't spread very much. So you generally can't predict. I mean, no one could have predicted 1918. No one could have predicted this. Although we have seen, as we destroy habitats where the bats live, where the animals live, as we eat some of these animals that live in the forest and as we invade their ecosystems, these things emerge. So I think Joe said it perfectly. If we don't learn from this, and there were lessons we learned from 1918, and there were things we did not learn. One of the most important lessons, there was a lot of misinformation, and it's a little more complicated. The government and newspapers were kind of in cahoots to convince people that this was just an ordinary flu when they knew better. And the cities where that was worse, nobody listened to any public health authority. But one city, San Francisco, stepped up and said, no, you guys know this thing is terrible. We don't understand it. And in that city, people behaved well, and they even volunteered to be ambulance drivers and to collect bodies. So we haven't learned the lesson about how to handle a pandemic. And I can only hope that we do this time. And we have been dismantling our public health structures since the days of Margaret Thatcher and Ronald Reagan. That has to turn around. And this is just, if we don't learn from it, shame on us.
Yep, I agree. I couldn't agree more. But I think with all these, leadership is important. Our leadership is important in putting us in the right direction. If you have leaders who send the wrong messages, including DT, unfortunately, things don't work the right way. But word of caution as well, the fact that I think hygiene is the key. Irrespective of vaccination, we still need to be on our guard, because I can tell you there are cases where, in fact, only yesterday, I had 2 colleagues in India who were vaccinated, had their second vaccination 3 weeks ago, thought they were completely protected, and therefore they went to a large society wedding without taking precautions. and they're both in hospital at the
Yeah.
moment.
Wow, that's interesting. I'm surprised they're hospitalized because we're finding that vaccinated people generally avoid hospital, but
generally, yes, I agree.
Yeah,
But
generally.
it's just a precaution. So you can still catch it. The severity will be less, but not for everybody. It just depends on how well protected you are. But I think partly because their immunization was only 3 weeks ago as well. And they were not,
Well, it's nonlinear. You tend to get, I mean, you really get your most protection after the first one in most people, right? Yeah. So, but it does happen, and I'm double masking everywhere I go. Yeah. I even double mask. That works. That is 92% as good as an N95 if you're double masking with the right materials. And I'm doing my best, but I've noticed in the US, which is the hardest hit country in the world right now, I'm telling you, people are they just have gotten COVID fatigued.
Yep.
And we never locked down as seriously as China or even Europe. We achieved 50% at our best. Now, China eradicated it with extreme lockdown, but they got to 90% at a moment when it was still doable. Lockdowns right now, there's a lot of evidence that they're not particularly effective because they're not very complete. So we have to, one thing I agree with you, and I'm glad you mentioned this, we all have to start thinking about if COVID does reach a low grade steady state, which I'm predicting, how are we going to all behave? Do we want to mask? I'm very aware of my environment these days. I notice how close I am to people, and I'm vaccinated, right? I feel a little protected, but I'm still very aware. And I think we're all going to have to develop that, and how that will change us as people and as societies it's all still something we're grappling with. Yeah. But as long as we're honest and trying to move forward, I think we're going to emerge from this, and I hope it will be better than when we went in.
Great. Thank you. Any other comments or questions? So
I'm seeing one question in the chat, and it's talking about whether there's progress in vaccines for children and pregnant women. And then also another question asking about the variants and whether we're protected by the current vaccine in Ghana against the variants. So I don't know if Karen will take one of them and I'll take the other.
Sure. Which one would you like to take, Joe?
I'd like to talk about the variants in Ghana. So we definitely have been able to show that aside the normal variant, we did have the UK variant in Ghana. But then looking really at the picture, I am sure we might have more than that in Ghana. So far, as I shown before, we have not too many people vaccinated in Ghana, and the measurement of the effects of the vaccine on severity of disease and admissions cannot be clearly shown here. But with a clear example of Israel, we have been able to tell that the vaccination works. And if it's working in Israel and we're using similar vaccines, then we expect that we should have a similar effect in Ghana. It would really be nice along the line to be able to judge how the immune system it's responding to the viruses, and then eventually the load on clinical cases that are presenting and the severity of the cases. So we're hoping as more people get vaccinated, we can get more information to give this concrete answer in Ghana. But if we mimic this to other countries, I think we should be protected against this, as long as we encourage everybody to take the vaccine.
And as far as clinical trials for kids and pregnant women, we've seen a couple of things now. The clinical trials, as soon as the first trials ended, they began trials on pregnant women. And vaccines, we know now that they're safe for pregnant women, and they're recommending them to pregnant women. Doing clinical trials of vaccines in children is far trickier, okay? You don't recruit patients in the same way, but they are testing. All the vaccines are now being tested in children. The vaccines most common in the US are the Pfizer and the Moderna, the RNA vaccines that are 2 shots. And I'm telling you, the side effects to these, they're a little more intense than to most vaccines. So that's something people are looking at with children, particularly vulnerable children. So stay tuned. I mean, there will be vaccines for kids, as there must be, because we know that the asymptomatic carriers, the median age of an asymptomatic carrier is 14. All right. So half of them are young, and they're the ones who are going to be moving it around. But if the older people are vaccinated, then okay, we're immune. They can circulate among us, but we really have to get on that too, and encourage people to understand that vaccination is the single most effective public health intervention we have ever developed in all of human history. And it's a wonderful tool. It's not a mechanism to sterilize or to, commit genocide or, all number of wild things. And one little tidbit I want to give you about this infertility. First of all, it only can apply to women because there's this crazy idea there's a tiny amount of homology with a placental protein. There were more accidental pregnancies during the clinical trials in the active vaccine group than the placebo group. So vaccination does not cause infertility at all.
Okay, great. So I will just add about vaccine safety. There is, in the UK recently, there has been an alert about the AstraZeneca vaccine where doses have been described in a small group of people. There's actually 79 out of about 20 million who have been vaccinated. And the cases have been looked at. Out of that 79, there have been 19 deaths, which is about 1 in a million of those who've been vaccinated. And so the actual occurrence is about 1 per 250,000. So the link is not proven, but it's been described. So we bear that in mind, and it's so far occurs more in younger people, below 30 years of age. So if you have headaches 5 days for, a few days after the vaccination, not on the day of vaccination, which most people do, then yes, by all means, seek attention. But we do not think it's anything to worry about unnecessarily, and that it shouldn't disrupt the vaccination program. But you will hear about it, which is why I'm mentioning it. But we do not think it's anything to stop the vaccination program. And most medicines, even paracetamol, has issues, unfortunately. Great.
I'm glad you brought that up, because one thing, you must think of vaccination as a public health intervention more than as an individual intervention.
Absolutely.
And you have to compare. If these 79 million people had taken their chances with COVID, there would have been far more deaths. So it's
Absolutely.
always a trade-off. Every vaccine has side effects, every medical intervention.
Absolutely.
Some people are harmed. We don't want to disguise that or pretend it's not true.
Yeah.
But life is a balance. It's about a balance of, death. Long COVID is a god-awful disease. We're getting a handle on some treatments, but
Yeah.
I fear long COVID more than I fear death, honestly.
That's right.
So always think, if there were no vaccine, how many would die or have long-term sequelae that are devastating. So, you know, no one is claiming there that no one will be hurt. We had a death we're investigating with the Pfizer vaccine. There was a case of thrombocytopenia. Now, is this a 1 in a million unusual genetic background that this one very healthy 55-year-old, he was a physician and he believed in vaccination till the day he died, right? What was that? Or was it a fluke that would have happened anyways? Our big problem with vaccination and seeing something is these things happen daily anyhow, right? People are going to get blood clots every day. Would they have had it without the vaccine? And that's an unanswerable question, but it's an important question to ask yourself and to reflect on as, you know, scientists.
That's right. And that's all the more reason why we should bring it out, talk about it openly.
Absolutely.
And because, like I said, even paracetamol has side effects. People die from taking overdose of paracetamol. And, you know, so it does happen, but we just need to put it in the appropriate context. Great. Any other questions, last minute questions or comments before we go?
Winfred, if I may, just a quick one. So on other systems, so there's this large study, 239,000 plus patients, where you know, the monitored patients, and over 6 months, it was observed that about a third of the patients had one or more out of 14 psychiatric or neurological disorders arising out of having been infected. I don't know the extent to which other organ systems are affected, but what have you observed? I mean, the clinicians and Karen, what have you observed in terms of the long-term consequences of having been infected?
It is variable. Yeah, so what you've described is right. So, which is what Karen referred to as long COVID. That, you know, there's a lot of psychiatric problems. Some people have, you know, the equivalent of post-encephalitis, aches here and there. And we believe that the long-term effects are not fully characterized yet. But it's
correct.
You know, it's we're getting better at it, but you know, we don't know the full details yet. But in the UK, the death rate, you know, 127,000 have died, as you know, from COVID. Those are characterized. There are other people who may have died that we don't know. So if 127 die in the UK, and you know, from COVID, and 19 die from a vein thrombosis that is associated with vaccination, I know which one I'll take.
Yeah, absolutely. And what's interesting, the coronavirus I studied was a murine hepatitis virus. It's mainly a gut virus, but it did have neurological potential. And I was studying it as a model for human multiple sclerosis. We absolutely know there are ACE2 receptors throughout the body. And estimates for people with longer term symptoms run as high as 30%. And I do want to mention the same thing happened with 1918 influenza. There were a lot of people, and particularly we know that the flu can become a neurological problem. It's not common, but that particularly bad flu did. So I think we have yet to see a lot of what's going to come down. I'm more worried, honestly, not so much the neurological, but I'm more worried about kidney and heart, because the receptor fields are denser there. And even if you've had asymptomatic, you could have damage that is right now, not because you're young and healthy. This may come out later. So I think we're going to be learning about this for many, many years to come. But this is it. There's more to this story than just an acute infection. And this is something unusual for viruses. This is not of the long hauler COVID. Boy, most virus infections are acute and resolved. So this is a different beast in many ways that we need to learn more about, but we're on it. Everyone who has anything to offer. And I want to mention something I just read yesterday about one thing we think about the long haulers, in case you know someone. There's some theory about what it might be doing is like there's a disruption in the signaling in the autonomic nervous system. And they've started with some long haulers trying to retrain that by doing yogic breathing. So breathing exercises are actually helping people. You know, it's not a complete cure of long haul COVID, but they're getting better energy and getting people's sense of smell back. They're training people, like they put like an essential oil that's fragrant on a cotton ball, and they have them smell things that have a strong scent. And it's helping them to get their sense of smell back. So we're working on it. We're making progress surprisingly fast, because this is where the state of medicine is today. I mean, every day I thank God that it's not 1918, right? It's, you know, that our tribe has done well for itself. We've had our problems too, but this is something we can take pride in.
Yeah.
As a tribe.
Yeah. Great. Thank you very much. So I would like to thank Karen and Joseph very much for their presentations and for fielding all the questions. I'd like to thank COBREG executive for putting this on, and there will be more of these to come, I hope. I'll hand over, on that note, I hand over to George. I shall put on my mask and make my way to my clinic.
Have a wonderful day,
Thank
Winfried.
you. Thank you.
Yes, Winfried, thank you so much.
Thank you all so much. Bye-bye.
Yeah, thank you all. Thank you all so much.
Nice to see you, Joe. Have a great day too.
Nice to meet you, Karen. Bye-bye.
Bye-bye.
Bye-bye. Bye. Bye.